The purpose of this video is to take you through a really quick exploration of the graphs of exponentials and logarithms. So what we have here is the graph of y equals 3 to the x. And in Desmos, we can always click on the graph and it'll tell us the ordered pairs for wherever we are. And what I want you to notice with this is that the graph continues moving to the right. It starts getting very, very steep, but it does continue moving to the right. And as I slide to the left, the graph also continues moving to the left forever. Okay, and what that should tell us is that the domain or the possible x values is all real numbers. And I'm starting to talk with my hands and you can't see me do that, but you can imagine it if you've sat in my class. So, and if I go over here to the function here, I should be able to reason that out, that I can put any number I want in for that x value. So I can put in y to the fourth, I can put in, x is equal to 4, so y is 3 to the fourth. I can say x is equal to 10, and you'll notice I start getting this very large number. I can make it x is equal to 100. Now I have 5.15 followed by 47 zeros. Really big. I could add another 0. And essentially what happened right there is that number does exist. You can take 3 and multiply it in 1,000 times, but it has exceeded what Desmos can think about. And so Desmos is telling us it's undefined. We want to recognize that as a limit of the calculator, not a limit of the math. Yep, same deal there. It's just got too big. The numbers are getting too big. Now, on the flip side of that, I can also make x negative, okay? And I can see that if x is -1, now I'm dealing with decimals. I could make it -5, and it's a smaller decimal, -10, and you can see that these decimals are getting really, really, really small, but they're not ever getting to 0. Now, I believe with Desmos, as with that undefined, it is eventually going to exceed Desmos's limit of like what it can process for numbers. So if you notice where the zeros are, we have like 4 leading zeros in that number. If I go to -50, now we have like 23 leading zeros coming in. And I have a feeling if now we have 34. I don't know how small it'll let us go. 48. Okay, there it goes. Now, it's not actually equal to 0, but it is so small that there were so many zeros in that number that yeah, we're down to like 238 zeros before you get to the 275. So it was actually getting so small that eventually Desmos says like we can't read numbers so small. But the point being is that you can plug in any value for x that you want. You can go as big as you want or as small as you want. And so the domain would be all real numbers. Now, what's more interesting is the range, which are the numbers you can get out for your y value. And we've already established that they can get really, really big. So if I put in like x is equal to 50, that would be like on my coordinate plane coming all the way over here to x is equal to 50. And when I do that, the number for the y value is 7.18 times 10 to the 23rd. Super, 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 super huge number. So I would have to go way, way, way up on the coordinate plane to find it. Okay, no interest in doing that really. As I go to the left, though, and I want you to notice this as we make our x coordinates, our x values smaller, okay? Y continues to be positive. So that is positive 0.00411. Now it is positive 0.0000169. Now it is positive. And now we have a whole bunch of zeros leading in, that y never, ever, ever becomes negative. And it's not ever really going to become 0 either. And what this is something in math called an asymptote. which is one of my favorite math words. It's called an asymptote. And this is a situation where you have the graph approaching a value, but never ever getting there. And so in this case, we have an asymptote at y is equal to 0. And so if I were to graph y is equal to 0 on there, okay, that is the horizontal line on the, I guess it's the x-axis. And what that means is that that graph has a horizontal asymptote. Horizontal means side to side. Asymptote at y equals 0. Now, if I were to say add 4, okay, we know from before that adding 4 to the outside of a function shifts it up 4 units. And now my asymptote has also gone up 4 units. So now if you were to make x smaller or smaller, the y value would actually be approaching 4. Now, because we want to keep it interesting, suppose I were to find the inverse of this function. And so we switch the x and the y. So we have x is equal to 3 to the y plus 4. The plus 4 will undo by subtracting it, and then we'll change it over to a logarithm. So log base 3 of x minus 4 is equal to y. So let's go ahead and graph that. This is actually y inverse. And I'll need to pull my log base from over here. So this is log base 3 of x minus 4. And just for fun, let's go and graph our line of symmetry. So let me, okay. And so as we saw in the earlier exercise, they are still symmetric over the line y equals x. So we have the red graph and we have the purple graph. But what I want you to notice with the logarithm, the graph of the logarithm, is where the graph of the exponential had a horizontal asymptote, the graph of the logarithm has a vertical asymptote. And so if I were to trace this, we would see that the y values can keep getting bigger and bigger and bigger and bigger and smaller and smaller and smaller and smaller, although we obviously have some limits to the graph there. But the x values are hitting this like wall right here where they're not really going, that is not, there we go. That's what I wanted to do, where they're not really going past the x is equal to 4. And so if I type in x is equal to 4, what we'll see there is a vertical asymptote. So the point of this particular demonstration is to, one, reinforce that symmetry, but also to note that exponentials have a horizontal asymptote, logarithmic equations have a vertical asymptote, and that the asymptotes would also have that symmetry over the line y equals x.